the discovery of a substance that changed our world, not with loud noise, but in the silence of a small laboratory in Berlin. Within the structure of these atoms lies immense energy, a force that, under certain conditions, can be released, and in other words, can be converted into energy or an unimaginable destructive power. Uranium, a material that today can supply all the electricity of a city, or it can become the most destructive weapon in history. Simply put, the history of humanity regarding nuclear physics has been full of ups and downs, and relatively dark. In my personal opinion, science alone bears no guilt in these dark pages of history. The problem is not in scientific advancements. The source of the problem, like all of history, lies in how humans use the power they possess at any given moment. In this video, we are going to find out how this raw uranium can be turned into a fuel that powers nuclear reactors. How long does it take to produce and process these high-energy materials? And what stages do they go through, from extraction to final use? How was uranium discovered? You might think uranium is as rare as diamonds or gold, but the truth will shock you. Uranium is 700 times more abundant than gold in the Earth's crust. In fact, the amount of uranium in the Earth's soil is roughly equal to metals like tin, which is used in cans. This means that, even as you walk right now, there are probably uranium particles beneath your feet. But they are so dispersed that extracting them is not easy. The discovery of uranium has an interesting story that dates back to the late 18th century. This element was identified in 1789 by the German chemist Martin Heinrich Klaproth. While experimenting on a mineral called pitchblende, extracted from silver mines in what is now the Czech Republic, Klaproth realized he was dealing with a different and unknown substance. He managed to separate a black powder from this ore, and, in honor of the planet Uranus, which had been discovered only 8 years earlier by William Herschel, he named this new element uranium. Interestingly, what Klaproth obtained was actually uranium oxide, and pure uranium metal was separated years later, in 1841, by Eugène Melchior Péligot. For more than a century, uranium had only one simple use: coloring glass and ceramics. People used utensils that glowed bright green due to uranium, without knowing that this material was radioactive. Then, in 1896, Henri Becquerel accidentally discovered that this substance had a strange power. He observed that uranium emitted radiation without any light source. This marked the beginning of the atomic age. But what makes uranium different from gold or iron? The answer lies in its energy density. The nucleus of a uranium atom is very heavy and unstable. When the nucleus of this metal splits, it releases an enormous amount of energy. To understand its power, it is interesting to know that a small uranium fuel pellet can produce energy equivalent to 1,000 kilograms of coal. Natural uranium consists of 99.3% uranium-238, which does not split easily, and only 0.7% uranium-235. More than 60% of the world's uranium is produced in Australia, Kazakhstan, and Canada. In the Canadian province of Saskatchewan lies the richest uranium mine in the world, where the ore concentration reaches 20%, 100 times higher than the global average. We said that the uranium found in the ground is mostly uranium-238. You might think that we can simply take uranium-238 and use it directly in a nuclear power plant or submarine to generate energy. Unfortunately, it does not work like that. Uranium-238 alone cannot sustain a chain reaction and is not a direct fuel for typical reactors. If we want to turn this metal into nuclear fuel, it must be enriched, and that is a very difficult process. You might wonder, if this metal is dangerous and toxic, and enriching it is also very difficult, why do we use it? Uranium produces no smoke when generating electricity and causes about 70 times less global warming than coal. In fact, nuclear power plants emit only pure water vapor into the sky instead of smoke. When uranium is purified into a metal, it appears similar to other metals, with a silvery color. The importance of this element is extremely high. When we talk about nuclear power plants, we do not mean only electricity plants. Nuclear submarines and ships also use the same principle to generate power. These vessels move using this energy. If their fuel is loaded once, they can operate for up to 30 years without refueling. The beating heart of a submarine or a ship is the nuclear reactor inside it. We said uranium has two important isotopes, uranium-238 and uranium-235. Uranium-238 does not have much direct application, but it is very abundant in nature, about 99.3%. Uranium-235, however, is highly reactive and very useful, but it exists only at about 0.7% in nature. You might say, this is easy. We just take uranium-238 and remove 3 units from it to make nuclear fuel. But it is not that simple at all. The uranium we extract from the ground is not even separated into uranium-238 yet. So how is this process done? This part is called enrichment. Let's go step by step through the entire production process to understand how uranium is extracted and enriched. 1. Extraction and production of yellowcake. In the extraction stage, drills with tungsten carbide tips, widely used in mining due to their hardness and heat resistance, extract uranium-bearing ore from the earth. These rocks are initially crushed and then turned into a fine powder using hydraulic hammers and semi-autogenous mills. They are mixed with water to create a uniform slurry. Next comes the leaching stage, where strong acids, usually sulfuric acid, are added to the slurry. This process separates uranium from the solid rock, dissolving it into a solution while waste materials remain solid. The resulting solution, containing uranyl ions, is purified and separated from impurities, turning into a clear yellow liquid. By adding precipitating agents, a paste-like solid called yellowcake is formed. This material, mainly composed of stable uranium oxides, U3O8, is calcined at temperatures between 400 and 700 degrees Celsius to remove moisture and produce a high-concentration uranium powder. The final product still contains natural isotopes, uranium-238 and a small amount of uranium-235. It is then packed into standard 2-10-liter steel drums and sent to conversion and enrichment facilities. 2. Fluorination stage. The process of converting uranium into uranium hexafluoride gas is usually done in several stages. First, it is converted into other oxides, then into uranium tetrafluoride, green salt, and finally into uranium hexafluoride. The reaction temperature for direct fluorination is usually below 550 degrees, around 250 to 300 degrees, although higher temperatures are involved in earlier stages. This gas is extremely corrosive, capable of dissolving even bone. 3. Centrifuges and enrichment. First, we need to understand what a centrifuge is. To simplify, a centrifuge has 3 main parts: a rotor in the middle, a rotating motor at the bottom, and a feed tube at the top. Uranium, in the form of uranium hexafluoride gas, enters through the feed tube. The motor spins at high speed, rotating the central tube. Using centrifugal force, the heavier uranium-238 is separated from the lighter uranium-235. The heavy molecules move toward the outer wall, while the lighter ones gather at the center. By repeating this process, the concentration of uranium-235 reaches 3 to 5%. For propulsion systems, like nuclear submarines, the enrichment level is much higher, so they can operate for years without refueling. The uranium is then converted back into uranium oxide powder and pressed under several tons of hydraulic pressure into small cylindrical pellets, about the size of a peanut. Number 4. Pellet and fuel assembly production. In a controlled environment, the enriched powder is pressed into small ceramic pellets. Each pellet contains as much energy as 1 ton of coal. Inspectors use microscopes and X-rays to check for tiny cracks. The pellets are placed into tubes made of zirconium alloy, capable of withstanding extreme pressure, high temperatures, and the harsh conditions inside a reactor. These pellets are baked in a furnace for 24 hours to increase their density and stability, a process known as sintering. Then, robotic arms place 200 to 300 pellets into zirconium tubes about 4 meters long. Number 5. Reactor stage and electricity production. The fuel assemblies are carefully transported to the power plant and placed in the reactor core, which can contain thousands of fuel rods, depending on its capacity. Nuclear fission begins when control rods are withdrawn, allowing neutrons to collide with uranium-235 atoms, splitting their nuclei and releasing more energy and neutrons. This chain reaction produces immense heat, turning water into steam that spins massive turbines, some tens of meters long at high speed. Each turbine generates more than 750 megawatts of electricity, enough to supply about 500,000 people. In the end, a rock that once seemed worthless deep underground becomes clean energy for cities, hospitals, and homes. 6. Spent fuel management. After about 1 year of operation, the fuel is considered spent. At this stage, it is so hot and radioactive that it must remain submerged in cooling pools at a depth of 26 feet for at least 10 years. The thick layers of water absorb its heat and radiation. Currently, millions of spent fuel rods are stored in such pools around the world under strict supervision. Going through this complex technical path shows that nuclear energy, beyond its scientific complexity, depends heavily on responsible management and proper site selection. History has shown that disasters like Chernobyl were not caused by the inherent danger of uranium, but by irresponsibility and ignoring safety protocols. The truth is that if a nuclear power plant is built in a safe location, away from natural threats such as earthquakes and tsunamis, and is operated under strict standards, it can be one of the cleanest and most efficient energy sources in the world. However, if neglected or built in high-risk areas, it can become one of the most dangerous forms of energy. All right, we have reached the end of the video. We hope you found this video interesting. Stay with us, and please press the subscribe button so you do not miss our future videos. Goodbye.